But today we're going to start with visual AI and medical imaging. And it's awesome to be able to kick off this series of medical imaging and visual AI and healthcare events, talking about it. And I'm going to start to try to do it at a very high level to go with. If anyone has any questions, as Jimmy mentioned along the way, drop those questions into the Q&A. But let's take a look at kind of visual AI and kind of the field as it relates to medicine and science as a whole, right? And we're talking about the classical sciences here. So if you weren't part of the spicy drama that happened towards the end of last year, there was a huge shakeup in the Nobel Prize community when in 2024, the Nobel Prizes for physics were granted to John J. Hopfield and Geoffrey Hinton for their foundational discoveries and inventions that enable machine learning with artificial neural networks. Now, this caused quite a stir, as you know, we have never given away a Nobel Prize in the past for AI, right? Especially not in like a math field, right? Everyone said, keep it there. Physics is for true physics. This is, this is the way science is done. And there's whole kind of battle lines that were beginning to get drawn on what side of should you get a Nobel Prize for this or not. One thing that certainly didn't make the conversation any easier was the next day for the chemistry Nobel Prize. Demis Hassabis and John Jumper shared the Nobel Prize in chemistry from the Google DeepMind team for their work on protein structure and prediction, or also known as AlphaFold. So this is just super spicy at this point. Everyone was up in an uproar. Clearly, science is no longer just this pure science where even at the very highest levels, we're seeing that artificial intelligence, machine learning can help you get to the points that you're trying to make, deliver better care, get better experiments. It's not all about getting the correct answer, but just running many simulations sometimes, being able to check many different possibilities in a much more intelligent way than we could in the past. So we can clearly see that AI is accelerating the research across the science community, as is reflected in the Nobel Prizes. So last year's Nobel Prize in Medicine, or the most current one, what was it? Was it AI? No. It was Victor Ambros and Gary Ruvkin for microRNA for post-transcriptional gene regulation. So why is this the case, right? We don't see the same kind of adoption. We don't have necessarily the same kind of publicity and stunts and Nobel Prizes being handed out in the medical field for AI as it results to medical imaging or anything like that. And how's that the case? Well, there's a couple of reasons, right? The one thing that we need to point out is it's more of a area that is primed to launch than it is an area that is lagging behind, in my opinion. Almost like a glass half full approach. What I mean by this is that key innovations are clearly being demonstrated in other fields, whether those are the tangential fields of physics and chemistry and some other fields like biology is having a lot of breakthroughs in artificial intelligence as well. And when it comes to the tasks that are associated to there. So why is it the case that we have not seen these big breakthroughs yet? Well, regulations and risk are slowing the progress, and rightfully so, right? This is not a critique of that, but it makes much more sense where I get a lot less approvals to run a physics experiment or a chemistry experiment than I would to have a medical experiment, right? There's going to have to be patients signed off. The data is harder to get. There's more regulations and risks to prove out the results. Just a harder thing to prove out and build up from those kind of regulated reasons. And this in turn kind of causes the academia as well to lag behind, right? So something that I don't hear in any other industry that I hear specifically in the medical imagery is if the hospital won't use it, then I won't build it, right? Because why waste our time? Like we have very specific grant money, with current administration and situations and things like that. Grant money is very scarce to come by. So you are building the things that are in most need right now. And if the hospital isn't signaling that the most needed thing right now is a new AI classification model or something along those lines, then a lot of times it's just not going to get built, right? There's also this significant disconnect between the patient care and the research being done, where you can be much closer to the end and start of an experiment in physics or in chemistry. For instance, if you're working in something like pharmaceuticals, you're not that far away from the research lab to the production lab, right? They're both maybe in the same building. But in medical care, there's hospitals across the world, clinics, doctors' offices, where you're not going to have that AI scientist down the hall to talk to, walk through how it works, how it might make mistakes, things like that. And so there's just a lot more processes to step through. But that's not to be said that there's any kind of sign of lag or if there's any kind of concern that this is not going to be something that is going to take off in a serious way. And the easiest way to look at that is that there's still many key industry challenges that AI can help, even without jumping too far ahead, right? Things just as rising costs, right? We talk about pharmaceuticals. Bringing a new drug to market, $2.6 billion on average to bring. Any way to drop that number, pharmaceutical companies will be more than happy to take, right? As long as they can do it safely and pass the regulations and go through their testing, that is something they're going to explore, and they are exploring right now of how AI can help speed up the cost or speed up the production and lower the cost for pharmaceuticals. That way, these life-changing drugs can hit the market faster. There's also a significant doctor shortage just worldwide, whether this is in our own communities or in communities abroad. The world just needs more doctors, and by aiding doctors with tools, we can help increase, when we go into the last point here, the amount of patients they see in a single day without decreasing the amount of care. One exact example here is on average, doctors are going to spend 16 minutes per patient scanning their record, right? Whether that is a medical imaging of a CAT scan or an X-ray or something else, it takes about 16 minutes to get to a diagnosis or at least a conclusive result for this scan. However, if with the help of something like AI, if we can help show them key areas of interest, if we can help show them maybe the 5, 10 closest scans to the scan you're looking at right now, we can help drop that number without overstepping okay, now the AI is making predictions and diagnosing and things like that. I don't think we're quite ready for that. We're probably not going to see that within the next 2 to 3 years, just for regulatory reasons and things like that. But kind of these new tools to point out like, hey, there's the pneumonia in the lung. It's right there, right? I'm not going to make the decision, but as the AI, I'm pointing at it. I think you should look here. And then the doctor can make that ultimate decision. As I mentioned, there's also these key research challenges, mainly in funding. There's also a significant issue right now with processing 3D and video data, right? Now, if you're following the trends coming off of the recent CVPR, 3D and video are hot, right? It is a lot of refocus going into here. How can we unlock both the temporal and the spatial elements of computer vision in a more serious way to get more accurate results? However, it's not an easy problem, right? Especially in the medical imaging world, where we are still working with, for the most part, medical imaging files. We haven't got into things like a Gaussian splat of a lung or something like that, right? Where we see that key interest in the community building up there, but it's going to come, right? It's just a matter of building out the tooling, things like that. If you're working in 3D, the amount of progress we've made 2 years ago from today is insane. Also, that comes with security and compliance of patient data. This is very classic, especially in America, where it's much harder to grab patient data, even anonymized patient data. There's a lot of people sitting on treasure troves of patient data, hoping to make some money off of it. And so it's not easy to get it every time. And then it's just tough to work with unstructured data at that scale. Whatever you're working with, millions of CAT scans, millions of X-rays, it's hard to kind of draw the lines through that are going to get you to the point that you're trying to make and make sure that your model is learning the most important things that you're trying to teach it. And that's what we're going to try to take a look at today, that last point. Because Voxel 51's vision is all about bringing transparency and clarity to the world's data. At the end of the day, nothing is going to hinder your machine learning system more than poor quality data. And the secret to getting any good ML project, especially in visual AI, across the finish line into production is by having a high quality data set, not by training a model over and over and over again. So we're going to look at some data-centric workflows, how they're being applied in visual AI, and how I've seen some open source users as well as enterprise customers use 51 to really accomplish extraordinary things in the medical field. 51 allows you to organize millions of samples in multiple formats, whether it's DICOM, CAT scan, or anything else, videos. You can organize them all in one place and work with them and help begin to find and eliminate false positives. Like I said, the moment that data in, the next step is trying to make that data set as best as possible. We can also help with things like the identification of patient data, dataset versioning, tracking all the different metadata coming off the machine, such as the manufacturer, scanning model, patient age, gender, all this kind of stuff, without getting too into the privacy details. Everything is going to run on-prem. Everything's going to be local. There's no security or compliance concerns, as everything's going to work with it. So how are people using it with 51 today? The first one is aided detection and diagnosis, like I've mentioned. Computer vision models are accelerating the scanning process and improving their accuracy. We have models such as NVIDIA's VISTA-3D. We also have MedGemma that is coming out recently to help with these kind of diagnoses and aid doctor whenever they're looking at scans for the first time. We can also monitor disease progression when you think about something like Parkinson's, right? If I'm doing segmentation scans of the brain, I can track how things like cancer, glaucoma, and more are all spreading or hopefully shrinking over time, to track that progress to make sure that there's no surprises and that we can always go back and understand how the disease has progressed over time through the aid of AI scanning of those medical imaging. We also have interoperable surgical guidance, robots working on patients to do real-time visual and spatial information processing in order to do the best possible care at the time. And we can also look at some of these live examples, and this is what I'm excited to show you today. So I'm going to hop out here real quick. I'm going to hop into one of my demos here. I see that we have a question in the Q&A, I believe. I don't know if that was answered away. Thank you, Jimmy. But we'll hop into the scans here. So here what we're looking at is some CAT scans. And so just to give you an idea, we have multiple different types of CAT scans for multiple different types of patients presenting multiple different problems, right? So very wide. We only have 50 for this example, but the total segmented data set has much more. So you can see that we have all different types here. Mostly around the abdomen area, but not all entirely around the abdomen. So now you notice though, that all these CAT scans have come off my scanner or multiple different types of scanners, and I can bring all my metadata with me, right? So I can see things like the age of the patient in here, right? And we can populate that if we want. We can also populate the gender, see if they're male or female. Also things like if it's an institute, the study type, splits, manufacturer of the model, that scanner model, all the good stuff that's going to come off of any classical scan information for the metadata could be brought along. And what's interesting about this is that we can now filter on any of this in 51 just because we've added it. So if I want to look at only the bleeding samples in my data set, I can find those bleeding samples. Likewise, I can find any of these. So if I'm looking for something like, let's say, tumors, I can pull up all my tumors and begin to understand. I can also click into any of these, play it, scan it, scrub it, however I need to, frame by frame, in order to understand the scan better, to see exactly what's going on here. Now there's an entire notebook, if you're interested in working alongside this, on how to load in data like this, carry all the metadata with you, and be able to visualize these CAT scans. But the important part here is how AI can help us, right? And so what we're going to do is we're going to look at two main workflows on how we can help work with this, starting with our model, which is going to be NVIDIA's VISTA-3D model. Now, NVIDIA VISTA-3D model is a foundational model for segmentation in CAT scans. We can see it is going to attempt to annotate not just the organs, but over 112 different bodily objects inside of your CAT scan, to help bring some labels to unlabeled data. Now, this model is about a year old. It's definitely not perfect, but it's a great step forward into what we're going to work with. We can see how it's going to get things like muscle groups, but you can see also here in some cases, it's not perfect, as we have face, for instance, where I am very confident that this is not someone's face. But we can see how the organs kind of pass through, understand the different areas. We can see the intestines come in, the spine, other different parts of the body. And help us understand a little bit more of what is going on in our data set. Now, the cool thing is that this model is available via API. You get some free tokens online. You can pass it in. It runs very quickly, and you can get some labels on top of it. I'm sure that they've done some fine-tuning on top of it to make it better. But this just shows you how you can do things like auto-labeling using VISTA-3D to understand more of your CAT scans, or how you can add your own ground truths, bring in your own model predictions, compare, evaluate, all on one place. 51 can hold any amount of labels, either on the entire data set or on the individual frames. That way you can begin to work with your data set however you prefer. The other really exciting part is that you can bring in embeddings as well. So here I have some video embeddings on my data set. Now, if you're not familiar with how embeddings work, embeddings are a representation of the medical imaging in a vectorized format. In this case, I have some video frames. So what I've done is I've computed embeddings on each one of the frames using a embedding model. And then I have concatenated my frames together in order to have a contextual understanding. And so now what we should see is that similar scannings should be closer to each other. This is great. So you can imagine if, let's say I am a doctor and I had a new scan come in, and it's going to be this scan here. So I have this one scan here, and I don't really know what's going on right now. I'm trying to make a understanding of what the pathology is here. With something like embeddings, it's possible to grab for this doctor the four closest other scans that have been previously diagnosed by a doctor before. And then we can begin to see how it works. And you can also color by whatever amount of metadata on top of this. So we can see here in our case, our scan had no pathology, and we pull our closest ones, and they also had no pathology. We have some questions in the Q&A. I'm going to answer them along the way. Anonymous attendee asks, the resolution of these CAT scans are too bad. Is that a matter of streaming? This is just a matter of the data set I'm getting from. There's no upper limit of resolution inside of 51. I can only work with kind of what I got, right? So there are other CAT scan data sets out here. You'll notice not all of them are terribly resolution, but in terms of working with them, it's going to be a matter of how much you store and how you've saved them onto your computer. High resolution is not a problem for us. Someone else asked, how is the similarity for the embeddings calculated in this case? Great question. So you can make a similarity index of 51 using our 51 brain. Choose the embedding model of your choice. It can be an open source one, or it can be one of your own that you're bringing along. And then we're going to do a similarity metrics based on things like cosine similarity, creating that index where it maps them all together. And what you're seeing here is just a UMAP representation, basically dimension reduction of my embedding space, right? But you can do PCA, TSNE, or whatever other dimension reduction form that you want to work with. That's all to say that once we have our CAT scans in, or whatever medical imaging you're working with, and you have your embeddings, you maybe have pathologies, you can begin to see hopefully what we're seeing here, which is that people that tend to have no pathologies are grouped together. There are some outliers here, such as some inflammation and some tumors that are sticking out over here. But those that do present different pathologies are going to be grouped together, right? And then now we can at least help the doctor by showing similar scans, help the doctor by showing that, hey, similar people, like this doesn't seem like a normal CAT scan. I flag this CAT scan as one that needs to have a close look. Don't, feel afraid to spend a little extra time on this CAT scan, whatever it might be, and how you're going to design that AI human doctor patient relationship. This is a nice step forward, at least from a lab setting, of helping build that out. But it doesn't have to be just CAT scans in this format. There's many ways to work with it. So we were mentioning some CAT scan issues in the past. Here's a different data set. In this case, we're also going to help with our labeling by using MedSAM-2. So in this case, we're waiting. And what we're waiting for is I'm actually going to pass in some ground truths of where I think this liver is, right? So you can see I'm responsible basically for one slice of the liver. But what MedSAM-2 is going to do is that it's then going to propagate forward all the different scans of the liver based off of that. So now I can help understand MedSAM-2 is fine-tuned. I think they'd be even fine-tuning it even more to work with any type of organ inside a CAT scan, where as long as you pass in what we call the prompt frame, we'll find it in this case too. You pass in that prompt frame, and then from that prompt frame, MedSAM-2 will help you propagate that frame throughout the entire body. This helps drop the annotation by a significant portion by allowing you to go from 2 detections essentially to much more detections, either blindly or by looking for all organs, looking for a specific organ. As you can see in the past case, we were only looking for the liver, but now we're looking for all of them. So it's very flexible. Also automatically built in with 51. All you got to do is pull it from our model zoo, and you can begin playing around with your own medical imagery. We do have a question in the chat that says, what is the value proposition for the doctor? Is the doctor relying on past cases information actively in determining a diagnosis? That is definitely a possibility, right? I think we just want to give the doctor as much information as possible to make a solid, correct, confident answer. If it's going to help the doctor to say, hey, if you want to see the 5 closest CAT scans to this one, and hey, all 5 of these people also had cancer or something like that, then maybe that's something interesting to the doctor, right? It's better than him trying to remember a CAT scan he saw years ago, or for him to try to remember something he learned in medical school. We're not trying to make the diagnosis for the doctor. We're not at that stage yet. But what we want to do is just equip him with the tools to make the best decision possible, right? 51 is much more on the model development side of that world for medical imaging, helping you understand how to evaluate, how to work with different detections, how to work with different medical imaging, so that way you can make those kind of understandings. It is not making these decisions. It's not going to be deployed in a hospital today or anything like that. It's more of the research lab model development side to help those who are building those relationships with the doctors and hospitals. So those are just to recap here. With one more question that came in, I'll get in a second. So just to recap here, total segmenter from VISTA-3D. If you want to check it out, we have it available on try.51. Also, we have an X-ray example. If you're looking for just a classical X-ray diagnosis classification example, we also have an example on try.51. But the last thing I want to show you, everyone, is MedGemma. Now, this has been recently added into 51 by my colleague, Harpreet. He has this on GitHub. You can scan this QR code. MedGemma is a new VLM that came out recently that can do not just classification, but VQA as well on medical imaging. And the awesome thing about this is it doesn't have to be just true medical imagery. It can be X-rays, CAT scans, pictures of people, pictures of skin diseases, diagrams, and you can begin asking medical questions in this context. So I believe I have an example for us to look up here. Let me go here. So here in this example, I have an example of all the different types of imagery and types of medical contexts you can work with for MedGemma. What we're looking at here, we can look in this case. We can begin to ask questions, VQA, add classifications for things like, hey, this is a dermatology resort. It looks like it's going to be this. You can also see that you can ask like what it is you're looking at. So even if you're just trying to clean up your database and add metadata to it to say, hey, I have this entire database of X-rays. They're not labeled on what part of the body they are. They're not labeled whether it's a break or not. You can also see this in. So we can see how MedGemma is doing things like diagnosing an ankle fracture. We can look at how it understands not just things like what exactly the diagnosis is, but it can also show not just medical imagery, but charts as well, right? So we can see how it's talking about all the potential conditions that are happening based off this chart, such as atrial fibrillation or ventricular block that are potentially showing here. We can see other diagrams. Basically, it can work with many different types. And we know these are accurate, right? So for instance, I am predicting here that this is a cardiovascular diagram, and it is also labeled as a cardiovascular diagram, right? So it is accurate whenever it makes these decisions. I really highly suggest you guys check out not just the model available in 51 for you to play around with today, but also check out the MedGemma page from DeepMind to understand all the different potential use cases, because there really is so many that I can't cover them all in one place. But with Harpreet's notebook, it's very easy to get started. All you got to do is make sure that you're logged into Hugging Face in order to access that model. Add that model to your 51 instance, load the model in. Note that it is 4 billion parameters, so it's pretty big. There is a quantized version that runs pretty fast, but just know you're probably going to need a CUDA device to do this. You can either do classification or VQA, as I mentioned, and then you can begin asking questions such as what medical conditions are visible in this image, or is there evidence of pneumonia in this X-ray? Explain your reasoning if there is, right? So really, really interesting stuff that you can begin working with this model and really exciting things of where the medical field is going. So I will pause on the screen. If anyone wants to get this QR code, feel free to scan it now. There's a bunch of questions that came into the chat, so I want to make sure I grab those. Lastly, always feel free to connect with me on LinkedIn if you're interested in testing out these models and have any questions, how you can get your medical imaging data set into 51 or how you can get started. Feel free to reach out with me, always happy, as well as I will always be pushing out any new medical imaging content as it comes out. We have a lot of our colleagues, such as Harpreet, who I've mentioned, but Paula as well, who are building up on this medical imagery workshops and webinar events that we're putting on throughout this week. So we're excited to bring all the fresh new medical imaging content from the best of computer vision to you guys. So give me a second here to dive into some of our Q&A questions. If you have any more, drop them in right now, as we are at the end of our slides here, and I'm happy to answer any questions. Thank you. So jumping in. Someone asked in the chat, can you discuss how we are currently conceptualizing how one facility will benefit from models and data trained off research conducted by another part of the world? This is a great question, right? So let's separate this question into the appropriate buckets first, right? Where there are people who have healthcare that is provided to them, and then people like in America where you have to get your healthcare insurance-wise from someone, right? Now, if you are in a healthcare situation where, let's say, Canada, right? It's much easier in some of these cases because the data is so widely shared throughout hospitals, right? This allows a lot of cooperation. It allows to find outliers. It allows to find the edge cases. That way we can try to build up the best care possible, right? It's very easy in those systems, albeit a lot of the other limitations potentially. Sharing of medical imaging is pretty easy in those communities to share this kind of stuff. Now, in America, most of the stuff is happening through Epic today. If you're familiar with your medical tooling, Epic is a company which builds a lot of the hospital systems today, including the ones that house records for hospitals. Now, as long as you are an Epic hospital, which most hospitals in America are, not all hospitals, you can share the different medical imaging across hospitals under a agreement that if I share mine, you'll share yours, that kind of stuff. But how that is being trained on AI and stuff, I can't speak to what the regulations are there today. I think it's very complicated. I think it's tricky. I think they're trying to figure it out. I think everyone's eager to figure it out. I don't think it is figured out. So I think to answer your question, in some geopolitical situations, you have many different environments. In other situations, you have very different looking environments, right? Now, it is absolutely important, though, however, to hammer home that we do train on multiple different medical imagery, right? We need to be making sure that we're representing all of our different communities, how everyone can look, how everyone is representing themselves, how to make sure that no matter where you're coming from, who you are, or what your background is, that you're going to get the best care possible. And even if that means that you have to find some care from across the world, if that's the best care, that's the world that we want to live in, right? That you're always going to get that best care no matter where it's coming from, and making sure that our models are trained on the best data no matter where it's coming from, right? As long as it's ethically and morally sourced, everything's being cut, security compliance, all that stuff that needs to come with medical imaging. I think that definitely should happen.